What is this?
We don't know.
Puzzle. It's a simulation of the Earth. Right? Small Earth, right? So if you go from Tel Aviv, which is here, to Los Angeles, which is somewhere around here, what is the shortest path? Yeah, okay, you go through it. It cannot, right? If you fly, airplanes cannot do that, right? What do? They can. גומיה, לוקח את זה ככה, נקרא עוד פעם, והגענו. טוב, לא הגענו, מטוס קרץ באמצע. בכל זאת הגענו. What is the shortest pass? That's right. Go through Greenland, right? So if you're ever wondering why airplanes, when you fly to America, go through Greenland, it's not because they want to take you to see the nice views. Because this is the shortest path, right? What is that? What am I showing? This is a geodesy. I'm going to go back to that today, so that's what I'm showing. Just in case you never saw it, right? So you saw this, airplanes that there's these maps that show you where you are, and it always looks like that they don't go in straight lines, right? Why do you see that? Why does it look like we're going in a straight line when you're?
Because when you project it onto a plane.
Exactly. Because the surface of the Earth is a two-dimensional surface, which is not Euclidean, right? And projection, the airplane is a Euclidean board, right? So it has to have some projection, right? And any projection, there is a theorem which shows that you can never do that. What?
The Oma Egregium.
What?
I think it's named the Oma Egregium.
Everly. You cannot. There is at least one point which you're going to miss, right? And normally when you do this, 2 points, like North and South Pole are being mapped into a line. Yeah. So that's a geodesy. Did anybody show it to you? What?
Offering pretty low.
Okay. That's what it should be. So that's why it's gives you the real distances from the surface. Okay. So, we are discussing vectors and tensors in curved space-time. Right, the bigger picture is we want to derive Einstein's equation. Einstein's equation tells us how mass or energy equal to mc squared acts to curve space-time. Before we can answer that, we need to know what does it mean a curved space-time. Before we do that, we need to understand how we work in curved space-times. Work in curved space-times. So space-time is curved, we have to accept it. And now we have to write physics in curved space-times. For that, we have the principle of general covariance. Yeah. Which essentially states that if you have an equation that you know is correct in the absence of gravity, and you know that it maintains its shape, so it looks the same when there's gravity, this equation is correct in general. Right? Which is great. That means that all the equations that we write in terms of vectors and tensors would be correct, which is what we want. But there are a few problems with that, right? Which is most equations will contain derivatives. Now we need to understand how we write this down. Before that, we argue that vectors in curved spaces are directional derivatives. Right? So a directional derivative is a generalization of the concept of partial derivative. So you have some curved space, which you call the manifold, right? You had a tutorial about that. So I know everything you need to know about manifolds, slightly more than you need to know. And there is a point P, and there is a curve, goes along with manifold, pass it through P. And we say a vector is the derivative along this path. So the vector V mu we would associate it with P over dx V. Okay. And covectors would be gradients. And we know how these vectors transform, which is essentially what they're supposed to be transformed. Right? So these are covectors. So V mu prime would be equal to dx mu prime over dx mu V mu. For covectors, omega mu prime is dx mu over dx mu prime omega mu. The tensors would be both. Yeah, question?
Yes, how does the definition, new definition of vectors coincide fit with the geodetic equation guide?
Wait. We don't speak about geodesics when we make this the definition.
We talked about the affine connection.
Wait.
Example of a non-tensor.
Yes, affine connection is not a tensor, not a vector.
Yes.
Wait.
And it's like
Patience. We'll get everything. We did not speak about a affine connection here. We just spoke about how to generalize the description of vectors, which we had in special relativity in flat spacetime. How to generalize it to any arbitrary curved spacetime. That's what we did, right?
in the metric tensor.
What?
In the metric tensor.
Same. Yeah.
How do you measure the distance left to direction derivatives?
Well, we spoke about volume elements, right? So the volume element,
Volume element defined.
invariant volume element, right?
Yes.
Square root of G, G and X, where G is minus the determinant of G mu.
How do this is how is the volume element defined using fixed way defined using derivatives?
Wait, I didn't find the derivative yet. You're jumping. One step at a time. Just follow what I'm saying. I mean, don't jump. You'll see that you'll get answers to all your questions at the end, and if you don't, come to me afterwards, I'll tell you what they are. But right now, we did not define derivatives. We defined vectors. We redefined vectors, right? And we defined a volume element.
My question is, how does the definition of the volume element look like a volume element when we do the definition of vectors and directional derivatives? How do you find a volume element for a few directional derivatives?
Well, it's written right here.
Yeah, I know it's definition.
You write down. You have a space, right? You describe the space by the metric tensor, right? G mu, right? And then you have your coordinates, right? You specify how you want to define your space, right? What coordinates? For example, if the space that you're talking about is the surface of the sphere, right? Then it makes sense to choose angles, theta and phi as coordinates. Then you know what are the coordinates. Then you know what is G, G mu nu. Then you can take the determinant, and you have a invariant volume element. You'll get an exercise on that. Don't worry. Practice it.
Theta and phi are in directional derivatives.
You can think of them as directional derivatives, yes, but that's not the problem. Direction derivatives in the directions of theta and phi, right? Yeah. If my manifold is like that, right? I'd say, okay, I have angle theta, and the vector in the direction of theta, right? It would be a vector in this direction. That's what it means. And the vector in the direction of phi would be a vector in that direction. It's perfectly fine. Right? We call this d theta and d phi. This is a minus here. And actually, no, it's a plus. X, y, 2. So this is a minus. Okay, bingo. Any further questions? Sure. Everything is clear? Actually, yeah.
That's where did it come
From the tensor of density. It's a weight on the weight. Essentially, it comes from the Jacobian. Right. When you're transforming G, you add up Jacobian to the minus 2.
Yeah, that's correct.
When you transfer the coordinates, you get 1 Jacobian. When you transfer G, you get Jacobian to the power minus 2. So when you take a square root of that, then they both 1 Jacobian and then minus 2 to the power 1/2 cancel each other.
Because G has dx mu, which is like 2.
Yeah, up to the power minus 2. That's the linear algebra textbooks, whatever favorite.
And when I see the same, a similar term minus G, just because of the convention?
You keep it, no, you can say absolute value, right?
It's the determinant and not minus the determinant.
It's a minus the determinant to get it positive.
So sometimes you find G just the determinant without the minus?
Because in flat spaces, the determinant of G will be a minus 1.
In both conventions?
Flat space, yeah.
No, but I mean the convention of 1 minus minus minus, or minus 1 1 both.
Same. We use here one convention. When you study quantum field theory, you get used to whatever. Okay, any further? No? No? Okay, so I said there are 3 things. So I said one of them was this volume element, which is quite cool. I even give you a demonstration that, in fact, you're doing that without knowing that. When you're asked to calculate volume element in non-Cartesian coordinate system. Now you can easily generalize it to any coordinate system. So we said one is the volume element, second is the Levi-Civita tensor density. So it's more to mention it, right? In flat space-time, I will denote it now with tilde. Flat space-time. Epsilon tilde mu1 mu_n was +1 mu1 mu_n are even permutations of 0 and -1. It's a -1 if it's an odd permutations, and it's 0 otherwise. Yeah.
I think you wrote epsilon 1, it should be the first one. But near the plus.
Ah. So this is not a tensor, right? That's called a Levi-Civita symbol. Levi-Civita symbol. That's the correct name. Why? What happens to that under coordinate transformation? Nothing. It stays like that. Right? It doesn't really care about the coordinates. So it's not really a tensor or anything. We can make it a tensor by, again, looking at the determinant of the Jacobian, dx mu over dx mu prime, and we can find out, so this does not change, this is independent of coordinates, does not change under coordinate transformation, as it is not a tensor. So to make it a tensor, we note, it's easy to say we know, you have to go and do it. I'm not going to do it for you now. Mu1 prime, mu(n) prime is dx mu prime over dx mu epsilon tilde mu1 mu(n) times dx mu1 over dx mu1 prime dx mu2 over dx mu2 prime dx mu(n) over dx mu(n) prime. So again, I'm not going to prove it to you because I'm lazy, but you can find it in your favorite algebra textbook. Surely all have it. Actually, know a few that do have it, but it's not in Hebrew. Hebrew ones. So what does it mean? What? So what do I call epsilon tilde? This is not a tensor. This is a what? This is how it goes under transformation of the coordinates. Right? There is an added Jacobian here.
Tensor density.
Right. Tensor density of what weight? 1. So this is a tensor density correct. So how do we make it into a tensor? Oh, come on, guys.
Find a transformation.
Yeah. What?
Divide by G.
Divide by G? What's the weight of G?
No, multiply by square root.
Multiply by square root.
Multiply by square root of G. Thank you, right? So we define, to make it a tensor, define, well, this is the Levi-Civita tensor, without the tilde, epsilon mu1 mu(n) is square root of G, epsilon tilde mu1 mu(n). This is a tensor.
Why is this expression
Why? What's the question?
why is this transformation being epsilon tilde?
That I tell you, you find it in linear algebra. That's transformation law of the Levi-Civita symbol.
Symbol.
Symbol will add up and one extra factor of Jacobian.
Symbol.
I'm not going to prove it to you.
Symbol always returns values of plus minus 1.
When you are transforming coordinates, that's what you're going to get. Epsilon in the new coordinate system. That's what you're going to get. Again, I'm not going to prove it to you now because I don't have time. If you want, it's just go to linear algebra textbook and prove it.
We will always get minus 1.
The value that you get in new coordinate systems, or different coordinate systems, will be associated with what you get from the old coordinate systems, times its transformations, times that. Just think of it if you want to have it in I don't know, Cartesian versus polar coordinate system. Further questions?
And the transformation, how does it look like? The same with the square root?
a transformation law here? Yes, then it will be without that. Just a transformation law of a tensor. I mean, this is, without that, this is a transformation law of a tensor, right? This is how a tensor transforms when we are changing coordinates. So when we multiply by square root of g, this is exactly what we get. And so this we can treat as a tensor. This, no. Guys, as I said more than once by now, there are things that you have to do a little bit more. So I could give it to you as an exercise, but I don't think there is a need because if you look at it in textbooks. And of course, we can raise indices as we want. We can use the same with an upper indices, and we get up with a tensor density of a -1. So by raising indices, this is just a note, raise indices, and then we get that epsilon mu1, mu(n) we define as a sine g, then we have 1 over square root of g, epsilon tilde mu1, and we want to use upper indices. That's it. Oh, I see it.
By sine g, you mean the sine of g, right?
Yeah. G is the determinant, and sine of g is the sine determinant. Yeah, I see that I put a note that even after I do that, this is still not a true tensor because in some manifold it will not. It will not be globally defined. Again, these are manifolds that we call non-orientable manifolds, and we don't really care about them in this course. It's getting more to have. Example of a non-orientable manifold is the Mobius strip. So you cannot really define epsilon globally, Levitz beta in the Mobius strip, but we're not going to deal with that here. That's more for the guys who like to play with the mass. All right? Okay. So that was that kind of small side. Now let's look at the main thing we're going to do today, which is covariant derivative. And can you erase that?
Just a question. Why does that raise the index?
Why does?
Why is it that what you wrote raises the index?
No, sometimes no. We often use epsilon with lower indices, but sometimes we find it handy to use in some textbooks, or sometimes we find it handy to use epsilon with upper indexes.
But if you want to raise the index, you should multiply by
G. Yeah, multiply by the G.
Oh, and
once this is a tensor, then everything, all the rules that you learn about tensors will apply.
can you get like this from multiplying by G?
Yes, you'll get that multiplying by G here. But then you'll have to have this epsilon tilde, you have to raise the indices of epsilon tilde. That's where you get this sign here. Right? The extra factor of the determinant you'll get, you have this extra G here, right? So this is 1 over G, which you'll get from the multiplication, and then this extra sign you'll get from really the transformation of epsilon tilde with upper indices. Okay. So let's do now covariant derivatives. As I said, physics is full of equations which contain derivatives of vectors. In fact, I think I don't know of any important physical equation in physics that does not involve derivative of vectors. This right now I can't think of any. The sad fact is that if we take a vector, we do a partial derivative of the vector, we're not going to get another vectorial of the tensor. So partial derivative of the tensor is not a tensor. So it is covariant derivative. So if we have a vector v mu, transformation law of v mu is v mu prime is dx mu prime over dx mu v mu. Now let's take the derivative of that. Derive. No, just derive. Don't need to say a long curve here. Just look at the derivation of that. Along x. Well, it is essentially it will be along the curve, right? Let's say along some coordinate x lambda prime. So the curve will be along that coordinate. So it's a partial derivative.
So in essence, we're deriving vector derivatives. We're deriving derivatives.
Again?
So it's in essence, since we're deriving vectors, the vectors are derivatives, we're deriving derivatives.
In a way, yes. It's a bit confusing, but yes. A vector is associated with directional derivative. Let's see. We'll get into that insight at the end of this lecture. dv mu prime over dx lambda prime. Is a what? d over dx lambda prime dx mu prime over dx mu d mu. So now we have to be a bit careful in how we do these derivatives because we have two different sets of coordinates, right? The new one and the old one, the primed and the unprimed. So how do we do that? dx mu prime over dx mu times dv mu over dx lambda prime, which we cannot do, so we can just do dx, we call it rho over dx lambda prime, dv mu over dx rho. Plus, now we have to take the derivative of the first term. So again, take the derivative with respect to the new coordinates, to the old coordinate system. So we have d squared x mu prime over dx mu dx rho times dx rho over dx lambda prime v mu. So if this derivative was a tensor, then that is what we'd expect to see, right? Because that's how tensors transform. Yeah? We have the second term. Ouch. So this is problematic. It's very problematic because we need to find the derivatives of vectors and tensors, right? Remember, for example, in the Euler's equation, I wrote it as T mu nu, comma nu. So I need to basically take the derivative of the stress energy tensor with respect to one of the coordinates, equating to 0. So this presents energy and momentum conservation.
Right hand side would be affine connection, right? It's right hand side.
It's not the affine connection, but you're right that there is something that looks similar to the affine connection.
Why is it less? Why
What?
is it the affine?
You're right that there is something here. So we need to find a way how to turn that back into something which is tensor. And for that, you're right that we need to have another look at the affine derivative. The affine connection. Sorry. When I write that, it's worse. You know what? Okay, I'll erase that now, and I may just write it back later. transformation law of the affine connection. Remember, I stressed the affine connection is not a tensor. Gamma, simple as they use lambda mu nu, is defined as the x lambda over d psi alpha d squared psi alpha over dx mu dx. What is the psi? What is it? Right. Locally inertial coordinate system. Okay, now we want to make a transformation. So we change coordinates from x mu, transform x mu to x mu prime. Okay. What happens to the affine connection? Let's see. Gamma, lambda prime, mu prime, mu prime. Now we write it in terms of the new coordinates. Dx lambda prime over d psi alpha, d squared psi alpha over dx mu prime, dx mu prime. I want to transform, so I want to express it in terms of the old coordinates. So I have dx lambda prime over dx, I'm going to call it rho, dx rho over d psi alpha. And here I have d over dx mu prime of d psi over dx mu prime, so I write it as dx sigma over dx mu prime d psi alpha over dx. So, what do I have? Dx lambda prime over dx rho, dx rho over d psi alpha. And here again, I need now to take this derivative. I have two terms here really. So, let's take the second one first. So, I just copy that, take the derivative of the second. So, it's d x sigma over dx mu prime, d squared or dx, therefore I call it tau, dx mu prime, d squared psi alpha over dx tau, dx sigma. Right, so I took the derivative of the second term. Plus, well, the first term, which is d squared x sigma over d x mu prime, dx mu prime, vice versa, d psi alpha over dx sigma. I mean, okay, I know it's happening, but it's really straightforward. You just have to follow the rules. There's nothing else. Okay, now what is that? That is the affine connection. So what we have here is dx lambda prime over dx rho, dx rho over d psi alpha. What did I do here? Oh, sorry. That times that is the affine, is gamma. So dx lambda prime dx rho, dx sigma over dx mu prime, dx tau over dx mu prime, and here I just have a gamma rho tau sigma. plus dx lambda prime over dx rho. Here I have a dx rho, d psi alpha, dx sigma, so this is just a delta rho sigma. So I can write it down as d squared x rho over dx mu prime dx mu. So, if gamma was a tensor, then when we make the transformation, this is what we'll get. It is not a tensor, so when we make a transformation, we get that plus this extra term here. Is that clear? Yeah? Okay. So now I'm going to do some algebraic manipulations, which is
So
yeah.
just to make sure I follow in the line before that, the affine connection is that second derivative in the parentheses.
This is the affine connection.
But like the way you got it is that you like the first derivative comes from outside the parentheses, and the second derivative comes from inside the parentheses. Right?
What?
So like in the affine connection you have.
I just wrote the affine connection in the new coordinate system, right? Prime system. Right. Then I said, okay, I want to express this in terms of the old coordinate system. Yeah. So just express them in terms of the old coordinate system. And d squared psi alpha dx mu is just d over dx mu of d psi over dx mu prime, which I wrote as dx over dx mu prime, d psi over dx. That's all. And then I took the derivative of that, so I have a derivative of multiplication. Yeah.
The order of the derivatives does not matter?
No. Yeah.
So it's,
Just have multiplication. Not just
no, the order inside the derivative.
Ah, no. It's a double derivative. I take a derivative with respect to one, and then with respect to the other. That's right.
But you can change the order how you take the derivative itself.
Yeah.
First
I actually
take
did that even
by
without
that,
it.
and after take by
Yeah,
that.
that's I think maybe there are spaces which is more
No, because
crucial.
you replaced the order.
Oh, here, everything I did is fine. Right? It's legal. Completely legal.
Yes. Only if you can change the order.
Yeah, but that's okay. Okay, so now let's do a little bit of. It's gonna be ugly, but it's algebraically ugly. It's not. There's nothing conceptual. So we have here this term. So this term I'm going to use dx lambda prime over dx rho over dx nu prime, use delta lambda prime nu prime. So using that, we got dx lambda prime over dx rho d squared x rho over dx mu prime dx nu prime is equal to. Yeah, okay, just take the derivative, the second derivative of that basically. So it's a minus d d squared x lambda prime over dx rho dx sigma over dx mu prime dx rho over dx mu prime. Just take the derivative of that, and from that take the derivative with respect to mu prime, and you just get immediately what you have here. Okay, see that? We need one more minute. Just take that and use d over dx prime. And that is a delta. I just took the delta and I took the derivative. That's it. Yeah, I have here minus. So basically, I just took this first term and I just move it to the other side. Took the derivative, I get here a 0. Second derivative here, and then this first derivative. So I have to add both of them. I just move it to the other side. Nothing really alarming. I told you, just a bit of algebra. And when I do that, I have the affine connection, which I can write as maybe the last line here. We have gamma lambda prime mu prime is equal to what we have here, dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime, gamma rho tau sigma. And instead of that, I write what I have there, which is minus dx mu prime, dx rho over dx mu prime, d squared x lambda prime over dx rho dx. Why am I doing all that? Now what happens when I take that and multiply that by the vector v, gamma lambda prime mu prime times v mu prime is basically I copy what I have here. Dx lambda prime over dx rho, dx sigma over dx mu prime, dx tau over dx mu prime, gamma rho tau sigma, minus dx sigma over dx mu prime, dx rho over dx mu prime, d squared x lambda prime over dx rho dx sigma. And v nu prime is dx nu prime over dx, I don't know, kappa v kappa. So dx sigma dx nu prime dx nu prime dx kappa is a what? It's a delta sigma kappa. So I have a dx lambda prime over dx rho, dx tau over dx mu prime, gamma rho tau sigma, and then delta sigma kappa v kappa is just v sigma. Minus, again, I have dx rho dx nu prime dx kappa, that's a delta rho kappa. So I have a minus dx sigma over dx mu prime, d squared x lambda prime over dx rho dx sigma v rho. I know it's ugly, but just algebra. Just have to follow very carefully over the algebra. We're nearly there. plenty of dummy indices, or indices that simply can replace their names. So I can exchange between mu and lambda. Let's do that. Every time I have a lambda, I'm going to exchange to a mu and vice versa. So this will be a mu prime, lambda prime, mu prime, lambda prime, lambda prime, mu prime.
Why did you do that? Why is it?
It's necessary? No, it's not necessary, just for, you'll see that, we'll just match in a second. Every time I have a row, I change to mu, and tau I change to row. This is the first term, it's a dummy indices. So row I change to a mu, and tau I change to a row. In the second term, row I change to a mu, and sigma I change to a row. After doing all this, I end up with lambda mu prime, lambda prime, mu prime, lambda prime, mu prime. V mu prime is dx mu prime over dx mu, dx row over dx lambda prime, gamma mu row sigma v sigma, minus dx row over dx lambda prime, d squared x mu prime over dx mu, dx row v mu. Okay, now come for your question. Yeah.
In the second to last line at the end.
Which line?
This,
That?
yeah,
This one, yeah.
So the last term,
Yeah.
the denominator of the second derivative, before you erased it, it says dou x k times dou x sigma, right?
Here, you mean?
Yeah. It's dou
This
x
was
k.
this was a d squared x lambda prime over dx row dx sigma. Yes.
And that v, before you erased it, it was 0.
And v was 0, yes. So rho was a dummy index, right? Rho is a dummy index, so I can rename it whatever I want. I choose to rename it with a mu, right? Now I had the mu prime, which appear on both sides, so it was just my choice, right? So instead of mu prime, I now decided it was not such a good idea. I changed it to a lambda prime. Just to confuse you, that's all. No, actually, it's not just to confuse you. Remember, there was this equation initially which I wrote and then I erased it. So I have to write it again. d mu prime over d x lambda prime is dx mu prime over dx mu, dx row over dx lambda prime, dv mu over dx row, plus d squared x mu prime over dx mu dx row, dx row over dx lambda prime v mu. Yeah, I wrote that when I just show you the derivative of v.
So you can just add it and then cancel.
That's why I did it, right? So now you can simply add that. And annoying term. So if I now take So if I now take dv mu prime over dx lambda prime, and now I add to that plus gamma mu prime lambda prime mu prime v mu prime is equal to dx mu prime over dx mu dx rho over dx lambda prime times only the first term is left, dv mu over dx rho plus gamma mu rho sigma v sigma, which means what? What?
It's a tensor.
This is a tensor. Very good. Very good. So now, you all see that? Because this is a transformation law of a tensor. So now, after all this algebra, and all this manipulating the indices, you see what I was trying to do here. That enables me to define what's known as a covariant derivative. So covariant derivative which is denoted as lambda, capital lambda, v mu, or another, remember I told you that, v mu, semicolon lambda, not the column, but semicolon, is defined as dv mu over dx lambda, plus, now it's quite easy to remember, gamma, I have two indices, upper and lower, so the upper will go to the gamma, lower will go to the gamma, then I have another index, which will be the dummy index, the sigma and the v sigma. This is a tensor, which is proven here. Because v mu prime lambda prime is dx mu prime over dx mu, dx rho over dx lambda prime, v mu rho. Nice, isn't it? What's the fine connection in flat space-time? It's all zeros, right? All components are zeros, right? How do you see that? What happens to the metric tensor in flat space-time?
Constant.
It's constant. And the affine connection is defined by the derivative of the metric. So it's all zero, right? So we have what? We have an operator that, in the absence of gravity, we get back the regular derivative that we're familiar with. With gravity, we have something else in curved spaces, but it transforms like a tensor. So if we take an equation and write it in terms of covariant derivatives rather than regular derivatives, according to the principle of general covariance, this equation is going to be true. Cool, isn't it? Guys at the back? Yeah? Happy? Okay, that's half of the story. What's the other half?
Actually writing the equation.
Oh, wait, no. Wait. We actually wrote some equations, especially with this. What's the other half? What about covariant vectors? Yeah. So what are you gonna do? Anyone want to guess? What's gonna happen? Okay, let's derive it. Covariant vectors omega mu prime is dx rho over dx mu prime omega rho. Let's take the differentiation derivative. D omega mu prime over dx mu prime is dx rho over dx mu prime, dx sigma over dx mu prime, d omega rho over dx sigma plus d squared x rho over dx mu prime, dx mu prime, omega rho. I'm going to go over that quicker because the algebra is essentially the same algebra, right? Just slightly other manipulations. And then we wrote it, I erased it, so that's so you just have to rely on your notebook, right? Gamma lambda prime mu prime omega lambda prime is dx lambda prime over dx rho dx sigma over dx mu prime dx tau over dx mu prime gamma rho tau sigma plus dx lambda prime over dx rho d squared x rho over dx mu prime dx mu prime. And then omega lambda prime, I can just write it as dx kappa over dx lambda prime omega kappa. So we're going to have this gives me a delta kappa rho. So I'm left with dx sigma over dx mu prime, dx tau over dx mu prime. Gamma, I have a delta kappa rho, so it's a gamma kappa tau sigma omega kappa. And here in the second term, I have a delta kappa rho, so plus d squared x kappa over dx mu prime omega kappa. What do I do now? I have these two equations, and what do I do? Huh? Subtract. Right, so now I subtract, and I get that d omega mu prime over dx mu prime minus gamma lambda prime mu prime omega lambda prime is dx rho over dx mu prime dx sigma over dx mu prime d omega rho over dx sigma minus gamma kappa rho sigma omega kappa. So from here we define the covariant derivative of the covariant vector. Lambda omega mu semicolon lambda is d omega mu over dx lambda minus, again, I have two lower indices, so I put them in the gamma, omega, and lambda, and then I put gamma index, sigma, omega, sigma. Right, this is the gamma index. And again, why did this not correct? Thank you. So this is a tensor. Since omega mu prime lambda prime is dx rho over dx mu prime dx sigma over dx mu prime, lambda prime, sorry, and omega rho sigma. Our wild guess. Is that clear to everybody what we do here? Well, it's pretty neat. How to convert a derivative into a covariant derivative. Vectors and covectors. Yeah.
Why is there a minus sign for the gamma?
What? Because I subtracted this. Right? With that, I subtracted that. So the minus here, and I add.
Yeah, but that's not what happened with the covariant. Where was the difference?
There's a contravariant and a covariant. Where's the difference? That's why I did this delta. That I thought there was this extra step that I do this dx lambda, dx rho, dx prime. This is the delta, and then I do the derivative. Go over the note. It's just so much.
Wait,
It was one extra step.
Covariant derivative of a contravariant.
This is covariant vector. This is contravariant vector.
Ah.
Again, covariant. When I don't say anything, I normally mean contravariant vector. I also call them simply vectors. When I say covariant vectors, I mean. Okay, if you got the idea, what's the covariant derivative of a tensor?
You get the plus for the upper index and minus.
Exactly. So for a tensor of any tensor, do quite well with the time. So if we have a tensor, it's quite easy, right? For every upper index, we get a plus gamma. For every lower index, there is a minus gamma. So for example, if I want to take the derivative of t mu1, mu2, and mu1 with respect to sigma, x sigma, this is the regular derivative, t mu1, mu2, mu1, comma sigma, or no, d over dx sigma, which is the same thing, plus, again, gamma, what's going to be in the gamma? So I take for the first term and the sigma. So it's mu1 sigma. Since gamma is symmetric, it doesn't matter where I put the sigma. And then I put a dummy index lambda. And then the t would be the lambda, mu2, and mu1. Now the second term, plus t gamma mu2 sigma lambda, t mu1 lambda mu1, minus gamma, what's going to be? So I have sigma mu1, the dummy index would be upper, so it would be a t mu1 mu2 lambda. Yes?
Is there such a thing as a contravariant derivative?
No, not that I know. Or at least maybe mathematically there is, but not in GR physics. Because again, we are deriving along a curve in space, right? And the covariant vectors belong to the cotangent space. So there is some abstractization there that I don't know if it has a physical meaning. Okay. So, what we did was basically we extended the concept of derivative curved spaces. Now, there are many advantages to covariant derivatives, right? They're not dependent on any specific coordinate system, so you can do it anywhere. They transform tensors to tensors. Okay, I will erase that. They are linear. So a few properties of covariant derivatives. So have linearity, namely alpha t plus beta s lambda. Right? Alpha and beta are numbers. T and s are tensors. It's just alpha t lambda plus beta s. So they're linear. They obey the Leibniz or the product rule. So Abla, I write it down in a different way, right? T external product of S is number T external product is S plus T is S. This is equivalent of writing Ts lambda is equal to T lambda S plus T S lambda. Right. It's the same, just written in different. Why? Check it out. Just the way it is. Just adding terms. That's it. What's the covariant derivative of a metric? What is G mu nu lambda?
I would guess 0.
Yeah, it has to be 0. Why? Why did you guess?
Because it makes sense for something to be defined in a way that kind of keeps the metric constant.
In flat space time.
In flat space time,
Covariant derivative turns into regular derivative. Derivative, what is the metric tensor? It's constant. So the derivative of the metric is 0. So the equation has to be the same. Now you can check it out directly. So this is dg mu nu over dx lambda minus gamma rho lambda mu g mu rho mu minus gamma rho lambda nu g rho mu. Now you can simply plug in the definition of lambda. You see that this is equal to 0. It's not surprising. That has a name, by the way. That's called the metric compatibility. What's the covariant derivative of the inverse metric? It's also 0. Covariant derivative of the delta function? Yeah, of course. What? Why should we? Because you know how it looks like in flat space. So the importance of covariant derivative at the end of the day, there are two things. Covariant derivatives one, convert tensors into tensors. Two, reduces to ordinary differentiation derivative in the absence of gravity. Absence of gravity, where gamma lambda mu nu is equal to 0. So together, we have the following algorithm. If we want to write an equation that we know is correct in GR, what do we do? Write an equation that is correct in the presence of gravity. One. Write an equation that is correct in SR, right? Write an equation correct in SR, no gravity.
Then change all derivatives to covariant.
Then change eta mu nu into G mu nu, and comma to, sorry. That's it. You have an equation, any equation. Like Maxwell's equation. You've seen that, right? We showed it to you in one of the tutorials.
Yeah.
Now you know how to write them when there is gravity. Yeah, questions? Good work. Yeah.
What if I have a space with a constant metric, which is not a standard metric? The gamma symbol would still be 0, right?
You mean non-Minkowskian metric?
Yeah. Choose a matrix and make it your metric, and make it.
You can transform it to a flat
What?
space. It can be equivalent to a flat metric. Actually, I think you'll see that in one of the. Then what? What's the problem?
I'm just asking if this is called absence of gravity.
Yeah. You can write down a Cartesian. If you write down a flat metric in spherical coordinates, it's
not
still flat.
Not flat metric.
It's still flat. Right.
But
Instead
not
of writing
writing a
Cartesian
flat
coordinates x and y, I can choose here r and theta. That did not change the structure of the manifold. The metric essentially is going to describe the manifold. We're going to get into that on Sunday. It doesn't matter. You just work harder, but you'll end up with the same equation. I mean, you can do a covariant derivative, but then the affine connection will be 0. If your metric is as constant, which is not -1 and +1, you want to stretch it. I don't know why. Take the derivative, gamma will still be 0. Right, so you do the covariant derivative, and you end up that it's equal to the. Questions? More questions? Yeah.
It's kind of general. The principle of general covariance.
Yeah.
Is there kind of an easy way? Like it's nice and it's easy. Is there an easy way to see why it should be true? Because it seems to me like, I guess, I have an equation. Well, it would be
you
nice
mentioned that it follows directly from the principle of equivalence. At the deeper level, that is an outcome of the idea that you are coordinate independent. Physics does not know anything about coordinates. That's quite a deeper level, and we proved it. I think I'm going to put my lecture notes today on Sunday on the website so you can read it again. But you go to the textbooks and read there. Yeah. Okay, now I'm going to go. There was another question that I was asked about. How does all that related to geodesics? Right, we started actually with geodesics. Even before that, I want to get a little bit of even more insight on what's going on here already. This is a crucial thing, very central to this course. Geometric interpretation. Of covariant derivative. derivative of a vector? It's a flat space-time. What is the derivative of a vector? I have a vector v at some point x alpha. This is x alpha. What does it mean taking the derivative of a vector? That is kind of associated to a question that you guys asked me. Easy now. More important things, yes. What does it mean taking the derivative of a vector? Right? So I have this vector at some point x alpha. Right? Then I look at this vector at a different location, nearby, here. X alpha plus dx. So this is v x alpha plus dx. Now, of course, the difference is infinitesimal. And again, I got no problem with that. I mean, this is flat space-time, right? But I got no problem in curved space-times because I said near every point, close enough, it resembles Euclidean space. Right? But how do I calculate the derivative? What do you do to calculate the derivative?
I should subtract them.
Can you subtract?
No,
No.
Flat space.
because they belong to different vector
Right.
spaces.
So what do? You really do two things. The first thing that you do is that you take this vector and you move it back to x alpha, keeping it parallel to itself. That's called a parallel transport. And then, so this is v transported at x alpha. Only then, the second stage, we use the parallelogram theorem, right? And then we look at the difference, right? This is delta v. So if you want to take a derivative, every time you take a derivative, that's exactly what you're doing. You might not be thinking of that very much, but that's exactly what you do. Right? There are two steps that you take. You look at the vectors at one point in space-time, another point in space-time. Then you are parallel transporting it back to its original point. And then you take the difference in the vector and you say this is the derivative. Yeah. Now what happened in curved spaces? Of course you do the same. But what changes? What's the difference?
Components of V when you do a parallel transport.
Right. The coordinates of the vector change when we are paralleling transport. Now it's very easy to see. Actually, I don't need to use curved space for that. Right? It's enough that I use flat space. Right? But I just describe it in polar coordinates. So this will be my polar coordinates. Now I take a vector here. This is my vector at the point x alpha plus dx alpha. And the components of the vector are those. And now I parallel transport it to another point, x alpha. Now the coordinates of the vector, components of the vector, sorry, are now different. Because, well, see it everywhere when you don't use Cartesian coordinates. Even flat space times spherical coordinates you see. So the point is that during the parallel transport, the coordinates of the vector change.
We define parallel transport.
No. It will be defined properly. But intuitively you can understand what it is. Right? So when we're taking a derivative, again, we have these two steps that we do. We first parallel transport, and then we take the differentiation. Right? And so when we do a covariant derivative of a vector. Right. V mu lambda. Right. It's dv mu over dx lambda plus gamma mu lambda whatever sigma. V sigma. Essentially, right, we have these two terms, right? What is this term, the first term? This is the derivative. This is delta v. What is this term? This is the change in the coordinates. Now I'm going to prove it to you. Right?
But how does it work with the polar coordinates? Because polar coordinates, it's also flat space, so gamma is zero.
I'm going to see that. Actually, gamma will not be 0.
Polar coordinates.
So again, the coordinate of the vector change. This is due to the change in angle the vector makes with the basis vectors. Now, when it's small, we expect some change which is linear in the vector, which means that we expect something of the order blah blah beta v alpha is dv alpha over dx beta plus something which could be separate gamma alpha beta gamma v gamma. And the question is, why is this gamma turns out to be exactly the affine connection? Right? It's not an obvious at first sight. And that takes us back to the question of geodesic. What is a geodesic? It's a straight line. Right? And you said this is defined as a path that minimizes the proper time. This is how we define it. But we can use another definition. This is a path that what? Goes back to that. What? What is this path? again, geodesic, let's say from US to China, take you nearly New York. From New York to China, I should include it once. It goes nearly elsewhere. Okay, right? It's right now. How do I define it? This vectorial interpretation. What do I know about this geodesic?
Zero derivative.
When parallel transport, it's tangent.
The what?
You get the same vector.
What? We can say that this is a curve that, what about the tangent vector to the curve?
Doesn't change.
It's always parallel to itself. So a geodesic is a curve whose tangent vector is always parallel to itself. Right? So I have 2 points A and B. I can have many curves that connect from A and B. Right? But if I go to the tangent vector of that curve, it's not going to be always parallel to itself. Right? It changes. Only along the geodesic, the tangent vector is always going to be parallel to itself. Yeah?
You mean that it's parallel to its different versions along with you? Like its components?
Parallel to it. Yeah, it's parallel to itself along the geodesic. Yeah, different locations. So if we call this tangent vector, call this tangent vector u, always u. So what is the covariant derivative in its own direction?
Zero.
Zero, right? So covariant derivative in its own direction. So we get covariant derivative in its own direction. It's a loud sentence because vector defines the direction. Right? Nabla u alpha is u beta, is what we wrote here, right? Is u beta times du alpha over dx beta plus gamma bar alpha beta gamma u gamma is equal to 0. Right? U alpha just dx alpha over eta. But we know the geodesic equation. But u fulfills the geodesic equation. So we have u beta du alpha over dx beta plus gamma. Now it's the real affine connection. Alpha beta gamma u gamma equal to 0. So we must have that gamma and gamma with support are the same. In fact, this is we can use that as definition of the geodesic. Which means that the geodesic is a curve. So an alternative definition of a geodesic would be the geodesic is a curve that its parallel vector is always its tangent vector is always parallel to itself. Geodesic, hold on a second. It's good. A geodesic is a curve that obeys u is equal to 0. Yes.
How is that geodesic?
This is this equation.
Yes, how is that a geodesic equation? In the geodesic equation, we have the derivative with respect to the proper side.
Yes. You can use it as u beta is dx alpha, u beta is du alpha over the tau. Right? So you can multiply it by, instead of d over the tau, I have dx over the tau. Perfectly fine. Yeah.
I'm confused by the term parallel to itself. Who is parallel to who?
Again, I have a tangent vector to a curve.
Yeah.
Every curve. If a curve is not a geodesic, it's not the shortest way. That means that I'm looking at the tangent vector to a curve, and in different locations along the curve, it is not necessarily always going to be tangent to itself. In fact, by definition,
Who is not?
the tangent
Show me the two arrows that are not parallel.
this and that.
Okay, so it's not parallel to itself at the beginning.
No, it's not parallel to itself. I can find 2 points along
Yeah.
the curve in which the tangent vector to these points are not going to be
Okay,
parallel
it's
to each other.
different points.
Different points along the
Okay.
curve, yes.
I was missing.
While along in a geodesic, the tangent vector to the geodesic is always going to be parallel to itself.
Yeah.
Again, okay. The airplane that flies me from here to, I don't know, wherever, Los Angeles. Okay, the new rubber. That's an old rubber. It's like too long in the center. Right? It's going to go in a straight line.
Yeah. No, I'm okay. It was a
So
language
it's
thing.
always going to be parallel to
I'm
itself.
always
The airplane is not
parallel
going
to
to go in these directions, right? That's what it means.
You're
Airplane is
still
going to go
parallel to
straight.
yourself at the same point.
But
I
it's parallel to the path. Right? It's going along the path, and it's always going to be straight. It's going along the path, it's tangent to the path, sorry, and it's parallel to itself.
Okay.
Can you show what happened to tangent vector not along the geodesic?
Yeah, I just showed it.
No, but on a sphere.
And what?
On a sphere.
So just go up and down. It's an airplane would go left, right? You know? I mean, you know, I can select. I want to go from here to I don't know, to Spain. I can go in a straight line, or I can go via Sweden.
How do you see that it's not parallel to yourself?
That's what I'm saying. I have a path. Right? It's always the tangent vector to the curve, right, to the path, but it's not going to be parallel to itself, right? It changes. But if I take what is parallel to itself, right? I'm going like that, and I'm going here, and just move them, they are parallel. If I'm going here and I'm here, I move it to that point.
But on sphere, when you move it, it's also
No. Parallel transported to itself, but I'm not going to get it's going to be parallel to the same one at a different location. We'll discuss that more next week. But that was just the alternative explanation. And that basically answers your question. That's yours. How is that related to? Okay. You had questions sometimes in the beginning of this lecture, which I promised you an answer before the end of this lecture. Okay, that's to give you some idea of interpret. Oh, we're running out of time. Okay, there are small things which are not going to be quite neat, showing you that we can write down. Since that you're familiar from vector analysis, such as gradient, divergence, scrolls, you can have very elegant ways of writing it. Okay, I won't take more of your time right now. We'll do that on Sunday. But the concept here, okay, so what did we do? It's actually quite important. So we generalized the concept of derivative to covariant derivative, which is true everywhere, which enabled us to write any equation that we know is correct in special relativity in the presence of gravity, in any arbitrary curved spacetime. And I gave you, the last part, I think this is an important one because it gives you some insight. What does it mean, this covariant derivative? And that actually also helps understanding why it's called an affine connection. Remember, I mentioned it, right? Because it connects points at different locations in curved spaces. All right? Any last questions for today? Since some people comment and ask, guys, normally when I give homework, it's for 1 week. I'll give it, since the system gives like a standard is a midnight, so that's why I give it 8 days. So it doesn't give you an extra day. It says if it's from Thursday, it's for next Thursday, so I'll give it Friday midnight. So until the end of the next Thursday. Okay, so don't get more confusion about that, or at this point you're supposed to know these things. All right, there was a question, yeah.
When you compare the affine connection of the derivative with the one of the geodesic, you skip the metric. You don't have to have a metric in that sense.
It's true in a way, yes.
So
if I want to calculate the geodesic, I do need a metric. I cannot do it without it.
Where in the geodesic you need the metric?
The affine connection. Here.
But there are affine connections which doesn't come from a metric.
Not that I know of. Affine connection, which we proved that mathematically. The affine connection is, you can get it from the first derivative of the metric, is associated, right, with the metric via the inverse metric and the first derivative. So let's say you only know the affine connection, you can, in principle, deduce what the metric that produced this affine connection was. That's in principle, because practically that can be quite a hard problem. We'll discuss that more when we discuss Einstein's equation in 2 or 3 weeks. All right. Any further questions? No? Then I'm going to post the next problem set today. And a good weekend. See you.
נכון, אמרת שהייתה בגאודזי, זה קו עם זמן עצמי מינימלי. עכשיו, אוקיי, נגיד יש לי... יש לי משהו כזה. במפ כזה, כן?
אוקיי.
אם יש לי פה נקודה.